Well, good morning, dear. Welcome back. This is lecture number 22. And today we are going to discuss the story of naive Bayes and generative versus discriminative models. You see, the other day we discussed about Bayesian formula, and we deduced from the very fundamental this formula. That means probability of y given x equals to probability of x given y times probability of occurring y divided by probability of occurring x. And they have a nomenclature now. You know, this probability of y given x is known as the posterior probability of class y given x features or attributes in our classification problem. These are the nomenclature you should be learning or habituated with. Py is known as class prior, okay, or the prior probability of the class, okay. Then px given y is called the likelihood of a feature x belonging to a class y, and px is the prior probability of feature, okay. So these are very simple description. In other day we discussed about evidence, okay, hypothesis. Evidence is just like our features, and hypothesis is class. So as long as you have noticed that as long as our x, y were single event, there was no problem. This is a formula which could compute very easily all kind of things, right? The conditional probability which could compute. But here, now say x is our feature, okay, is a vector, feature vector. For n number of features, it could be like x1, x2, okay, x3, xn. So now this is not a single event feature, okay. Feature is n. N could be say 1000, 2000, 3000, 4000, okay. It's large, 40,000, okay. And y is again class. For binary class, y actually could be 0, 1. For multiple classes, 0, 1, 2, 3, 4, 5, like that, okay. So those are no more, those quantities x, y are no more a single event, rather they are fragmented. This event space is now fragmented, and which we discussed earlier. And then the problem is the formula takes a very ugly shape like this. If you want to compute using Bayes formula, then probability of occurring x1, x2, x3 up to xn given a class equals to probability of occurring x1 given the class, okay, prior multiple times the probability of x2 class prior y and x1, then probability of x3 given y, x1, x2, like that up to probability of occurring belonging a feature xn to a class y, x1, x2, x, and this probability distribution incorporates so many parameters to be evaluated, which makes computation very, very difficult, if not impossible. And then what we do? The engineers always do all kind of things, assumption, okay. We assume that the events, the event space of feature, that is featured, okay, are conditionally independent. So if it is independent, then x1, x2 and x1 independent, then x2, x3 independent, then this formula can be written in a computable form, okay. This is called naive Bayes assumption, that is the features are conditionally independent, then this is the probability of occurring this feature given a class equals to probability of belonging feature x1 to a class y times feature x2 belonging to a class y dot dot probability feature xn belonging to class y, and this could be modeled, and this is actually called naive Bayes assumption. The term naive is here because of conditional independence assumption. Because why it is called naive? Because the ground truth could be far from it. For example, you are we will discuss, you are using naive Bayes model for spam classifier. Their words are features, and in a spam mail there are words, they actually are not independent. Okay, and in many cases this conditional independence assumption are far from the ground truth. But even then, because of the simplicity of computing and finding the probability density functions, okay, assuming again some distribution is easier, that's why we use naive Bayes formula, okay, and it gives reasonably good results. Okay, so naive Bayes and Bayes formula, the difference is, I believe, clear. Okay, now let us go forward and we'll discuss now generative versus discriminative models. Okay, so far whatever model we have studied, for example a linear regression, logistic regression, they are known as discriminative model. What they do actually, for example, the linear regression, we have data, okay, and this is y, this is x. We had data and we were actually trying to fit a we are trying to fit a regression line. Okay, so we are running gradient descent algorithm, and this line started from somewhere, say from here, okay, 1, 2, 3, or it may start from here or here, and it will settle down. It will settle down to a gradient descent algorithm will make sure that it settles down to a decision. This is decision boundary, to a place where the prediction becomes error-free, errorless. Okay, so this line actually was moving here and there before settling down it here. Okay, so this type of model called discriminative model, because it was trying to look for each sample the true level. Okay, and likewise in case of logistic regression also, say it's a binary classifier, say I have two classes, okay, and the decision boundary actually could start from here, okay, and you are running gradient descent algorithm, or it could start from here, you are running gradient descent algorithm, eventually it is fluctuating here and there, and then when parameters are converged, then it makes a optimum decision boundary. Okay, so that was the nature of the discriminative model. You are directly calculating, given a feature, which class it belongs. Okay, giving a feature which class it belongs, or here in case of linear regression, given a feature, what is its level. Okay, so that you are discriminating from class to class. Always you are discriminating. Okay, and then you are finding the answer. In case of generative model, instead we do the following. We calculate probability of occurring a feature of a feature belonging to a class. Okay, so and we try to develop this model, and we also from the sample, and we also try to calculate the prior class probability from the sample. And after making this model, after generating this model, okay, we calculate that is discrimination, that is prediction we do. That is, now this is the part of training. So during training, which we are doing, we are trying to generate this model. That is, we are calculating what are the features supporting a particular class and prior of this class. Okay, so this is essentially the difference between these two. I will try to explain with some intuitive examples. Say I have several classes here. This is different kinds of fruits: apple, mango, banana, orange. Okay, and say fictitiously one feature I could show you. That's why I have taken one feature, distribution of one feature from here, from here, from here. Say it is a texture feature, maybe. Okay, just assume. So apple has, so here what is the assumption? Assumptions are very vital assumption that all the features, they follow Gaussian distribution, okay, or normal distribution. Okay, so this is a feature, say some features. So this is representing apple, this is representing mango, this is representing banana, this is representing orange. Now suppose a robot has come with a camera and a new fruit has come, and it could extract the same features distribution from here, and then what it will do? It will try to just calculate this one. Okay, so this is actually generating the model. Okay, after generating the model, it is calculating that now a feature has come. What is the probability that it belongs to apple, orange, or these categories? How? By computing the probability that given these features, what is the probability that it belongs to class apple? It will get some probability, say P1, okay, and P apple, okay, and then it will calculate P mango, then P banana, and P orange, say. So same fruit, the new fruit, these are the probabilities. So I will see what is the maximum value, okay, maximum of this, maximum of these values, okay, definitely will be the class where it should be categorized, because that's the class where this feature is similar. Okay, so this is essentially how the generative model make a prediction. And you can see similar kind of thing in case of your animals. I have not binary class, 1, 2, 3, 4 classes, and then I have similar kind of thing, okay, some feature, distribution of the feature. So here essential assumption is that features are following normal distribution. Okay, and then this is a new animal, then you can categorize. Okay. So prediction, which intuitively I have told you, okay, can be calculated by a function called argument maximum function. Okay, you are calculating the given a feature, you are calculating all the probability, and for what y this is maximum, you put that feature in that particular class. And I believe argmax function you know. If you don't know, then I will give an example. Say I have a function, f of say y equals to 1 by 1 plus y minus 6 square. Okay. So for what value of x, what will be the max f of y? So for what value of y, this function will be maximum, because this maximum value of this is minimum value of this is 0, because this is in the denominator. It has to be 0 to get maximum of y. So the value will be, this is 0, this is 1, so maximum value will be 1. But if I just ask you argmax, so argmax of that function, that value will be 6 over y, because when y equal to 6, then these functions attain the maximum value. Okay, so this is the argmax function all about. Okay, Now, how to develop a Gaussian, now we'll discuss, since you now know generative and discriminative models characteristic, we are going to propose a model known as Gaussian discriminant analysis based model. Okay, an algorithm is known as Gaussian discriminant analysis algorithm or GDA algorithm. Okay, we propose here, and this GDA is actually developed when you have less data. Okay, and your assumption is very valid on the ground truth of the data, that is features are continuous random variables and they follow multivariate normal distribution. Okay, and class prior, okay, follow Bernoulli distribution. Class prior y belongs to two classes. Okay, then we can actually develop a model which is very beautiful model, very simple model known as Gaussian discriminant analysis based model. So you see here the writing the probability, these are the probability density functions. Okay, I have assumed that my classes are following Bernoulli distribution. So this is probability density function of Bernoulli distribution. Okay, and what extra I have assumed that x, the features are continuous random variables and they follow Gaussian distribution. This is multivariate. This is the formula for multivariate Gaussian distribution. Okay, so here parameter phi needs to be evaluated from sample, which is a part of studying. You can call it a training process. And here the parameters mu and sigma is the variance need to be figured out from the sample. Okay, but you are habituated with one-dimensional single variable normal distribution. This is how it looks like. Multivariate Gaussian distribution is similar. Okay, here in place of 2 pi, okay, sigma square, this is what you will get. Okay, this is the variance. Okay, sigma square, it comes out, and n by 2, then e to the power 1/2. This is actually written x minus mu transpose inverse of this. Okay, so this is eventually your okay. So these are for one single variable, but you will have to be habituated that these are basically the same. You know the linear algebra a little bit also, and you will be able to know what it is. So these are now vectors or matrix. Okay, so let us see for n-dimensional feature vector what will be the dimension of this. So this is a real number, because determinant of the matrix of variance. Okay, x minus mu is a m cross n dimensional matrix. Okay, because x dimension is n, I have elaborated it. Say this, I have m number of samples. Let us call it, this is I equals to n and j is feature. Okay, and we have n number of features. So I equals to 1, 2, 3 up to m, and j equals to 1, 2, 3 up to n. This is number of feature, number of samples. Now I decide that okay, I will write X matrix like this. This is feature number 1, and feature number 2, feature 3, and this row is sample 1 and for n feature, sample 2 n feature, like sample n m feature. Okay, so row, there are m number of row equals to number of sample, so m cross n. However, since it's a matrix representation and representation in your hand, you can also this instead of making this as row, you can make it as a column. Then in that case, it will be dimension of the matrix will be n cross m. But whatever you do, you should follow the same procedure, because mu will be also same dimensional matrix. From the sample, you will have to subtract mu from each accordingly. So mu dimension and this dimension should match. Okay, and sigma inverse is a n cross n dimensional matrix. Okay, so this is multivariate normal distribution. This is how multivariate normal distribution looks like. Okay, and we'll use it for our GDA model. Okay, you see, once you have the model, okay, that distribution, Bernoulli distribution, multivariate Gaussian distribution, what you need to do? You need to figure out these parameters phi, parameters sigma, parameters mu from the sample. Okay, so how to do that? Again, same old story. Maximum likelihood estimate principle will apply. So we'll constitute a function L, likelihood function. What is the value of mu and sigma? This is, I have giving an example with single variable normal distribution, for example, and you have two parameters mu and sigma. Okay, given the samples. Okay, this is equals to likelihood estimate of mu sigma given x1 up to m number of samples. Okay, so now I know this, okay, because it's a normal distribution, so I can write it down, and this is into multiplication time multiplication. So this is the once you assume that distribution is normal distribution, I can do that. Okay, for getting, and this is an ugly equation, isn't it? Ugly expression. So how to evaluate that? Okay, for evaluating that, you will have to take log. Okay, because log will transform this multiplication sign into plus sign, and which is easy for you to calculate. Okay, so we are taking the log, which is called log likelihood estimate of mu, okay, and sigma. So taking log, I am calling that function new function with log of capital L. New function is known as small l. Okay, this is notation I am using, and this will be eventually can be written in terms of summation of this plus this, because log to the base e. Okay, log to the base e. So this is very simple. Okay, so this multiplication will be converted into addition. Okay, and you will have some terms which can be simplified, and once you have got a simplified function, then you can differentiate this function with respect to mu, because I want maximum likelihood estimation for the mu. Okay, so eventually we will get mu equals to summation of I equals to 1 to m xi by m. This is as you see, this is average. Okay, so but that average is coming, root is here. You must now at this stage remember you are calculating maximum likelihood estimate of mu. Similarly, the variance, how to get the variance? Maximum likelihood estimate, this function you have now, differentiate this function with respect to sigma. Okay, make it to 0, and you will get a sigma value. Okay, and then you can square it, because square root of x minus mu square, like that it will come, and you can rewrite in this form. Okay, okay, and then same thing for features. You have got this, and this is for class. We have assumed class follow Bernoulli distribution. So this is the probability density function for Bernoulli distribution. Here I need to calculate phi. Phi again can be calculated from the maximum likelihood estimate. Okay, and that can be just like earlier. This is the computation for probability, which is again multiplication. So you take log, that's called log likelihood estimate of phi. Okay, so what you do, you just take log, and log of this is actually transform it into this. Okay, so now you can just, you have log of phi plus 1 minus y log of 1 minus phi. Okay, so now you make this function. Okay, this is small l function, is a function of phi. You need to estimate maximum likelihood estimate of phi, so you need to differentiate with respect to phi, making it to 0, you will get the optimum phi, which is nothing but 1 by m times I equal to 1 to m yi. That's great. So you have got all the parameters now from maximum likelihood estimate. Okay. And one beauty of this GDA is, you see, whatever dimension of the feature might be, they are very, very computational friendly, because you have, once you have the sample, you can calculate. So this is, you have samples now, right? So 1 by m I equals to 1 to m, this is called indicator function. That is, whenever y equals to 1 for class 1, you put here 1. For y equal to 0, you put 0. Okay. So, and divided by the total m, okay, which you got from maximum likelihood estimate. So this is completely, once you have sample, suppose 50,000 samples you have, you can calculate phi. You can similarly, you can calculate, you have two classes here, right? Class 0, say mango and apple class. Okay. So mu 0 will be equals to indicator function 1. Whenever y equals to 0, then it will be 1 divided by 1 y equals to 0. Okay. Then similarly mu1, this is mango and mango class, for example. So you can calculate the mean of mango class, you can calculate class prior this parameter, and then you can calculate sigma as well. Sigma 1, sigma 2 individually you can calculate, but normally it is assumed that across the class the variance are similar. Okay, mu may be different. Okay, variations are same, but you need not follow this. You can just get an experience, but by making, because for calculating sigma 1 you have all these things, right? You have sample, you have mu, corresponding mu, you can calculate sigma 1, sigma 2, but it is practice to assume them to be same. Okay, so once you have got this parameter fixed, then what? Then the distribution is known to you, and then you can do the prediction. Okay, so once you calculate all the model parameters, okay, and then model, this is actually the training process. Determination of the model parameter is your training process, and then from base rule you can calculate using argmax function. You can calculate the given a particular feature, okay, in which class it belongs. Okay, and normally this is sorry, for okay, for calculating the argmax function, this is not necessary to compute, because this will be a constant as it has been illustrated here. This is a prior probability of feature, which is equals to, you have two classes, right? You will have to calculate the probability of this plus probability of this. Okay, and this actually is not contributing. This is a constant term. For any class you calculate this, it will be a constant term, same term, and then it will not contribute in determining the argmax function value. So that's why we ignored this to simplify our computation. So you know, if you have a given feature, from now you know the distribution completely, because all the mu, sigma and distribution is normal distribution, everything is known. Here you have the parameters, Bernoulli distribution parameters are there for that feature. You can calculate everything. This is analogous to pictorially, which I have told you, that you are calculating these from here, probability here, probability of this feature belonging to this, feature belonging to this, and whatever is maximum, this feature belongs to that class. Okay. So with this, I think the basics of, not basics, the GDA algorithm is completely known to you. This is a generative model. When samples are less, you can develop this model, and you can use this model as a classifier, and it works at par with logistic regression classifier. Okay, but your assumption should actually reflect the ground truth. The samples which you have, feature samples, they should follow the Gaussian distribution, and the assumptions are there. Mostly the features are conditionally independent. Okay, with this I conclude the explanation of GDA, and then I will formulate I have already formulated a problem, and I will share with you in the discussion forum, and in my site it will be there. Please do that problem, then things will be digested properly. This is one of the most elegant and simple to understand model. Thank you for your attention. Stay safe. Bye bye.